This is video 4 in the topic 10, how does a compass work? In this video you're going to be introduced to electromagnetism, and then we're going to be looking at in detail at how to calculate the force on a charged particle in a magnetic field.
In this video we're going to be looking at the theory of electromagnetism. Now this is going to be important for this topic, but also for the next topic in which we're going to be looking at nuclear power plants. Electromagnetism is responsible for being able to convert the energy generated by the nuclear power into electricity, which gets sent out to our homes. The discovery of the theory of electromagnetism was very exciting for physics. So before the 19th century, it was not understood that electricity and magnetism were linked. It was thought that these were completely separate phenomena. Then in 1820, Hans Christian Ørsted observed that if he had a strong current flowing through a wire and he moved a compass needle through it, the wire actually deflected that compass needle, which was an indication that there was a magnetic field associated with a current flowing through a wire. Now this wasn't really fully understood until in 1864, James Clerk Maxwell came up with the theorem of electromagnetism. Maxwell's equations can be written very simply. Here they are. There's just 4 of them. Aren't they beautiful? There's probably lots of symbols here that you've never seen before, and don't worry, you don't actually need to understand what all these symbols mean for this course. If you wanted to go on with more physics, then eventually you'd start looking at these theories in more detail. But this is just to show how beautiful and simple this theory is. And Maxwell's theorem of electromagnetism actually linked electricity and electrical forces with magnetism and magnetic forces, and also with light. He realized that light was electromagnetic waves traveling through space with the speed of light c, and he explained why this speed of light is so important in his equations. So it's actually been the holy grail of lots of physicists since Maxwell to come up with a grand unified theory in which they combine all the forces of nature. So Maxwell combined the electricity force and the magnetic force, and physicists now want to combine what's understood as the 4 fundamental forces. We've got the electromagnetic force, the strong and the weak nuclear force, which we'll be looking at in a bit more detail in the next topic, and the gravitational force, which you've already looked at a bit. So far, physicists haven't managed to succeed in this. They've managed to combine 3 of them. So they've managed to combine the electromagnetic force with the weak and the strong nuclear forces. But so far, combining gravity into a unified theory has eluded physicists. But there's lots of people working on it. So in this topic, we'll be considering the forces felt by a charged particle in a magnetic field. Now what I have here is known as a cathode ray tube, or historically it was known as a Crookes tube after its inventor, William Crookes. A cathode ray tube consists of a glass tube here which is completely evacuated, so there's a vacuum inside this tube. Now down the bottom we've got what's called a cathode, which is like a negative electric terminal, and up the top we've got an anode. Now what happens in this cathode ray tube is that electrons are released from the cathode and they then travel upwards towards the anode. Now you can't actually see electrons because they're tiny, so what we've got inside this cathode ray tube is a phosphorescent screen, so that when the electrons hit it, the phosphorus atoms actually end up releasing little photons, and we can see those photons as green light. So this allows us to see the electrons inside the cathode ray tube. So now let's just turn out the lights for a minute, and you can observe what happens when I move a magnet near this cathode ray tube. Because remember, it's just electrons, which are charged particles in here, and let's see what effect a magnetic field has on these electrons. So here you can see the electrons very clearly in the cathode ray tube. What I'm going to do now is bring the north pole of the magnet towards these electrons. Can you see how they are all deflected off to the side? Now let's try moving the south pole of the magnet towards these electrons. And now you can see they're deflected off to the other side. So south pole towards it, north pole towards it. And so this tells us that these charged electrons are feeling a force in a magnetic field. So we've seen what happens to the electrons in the cathode ray tube when we applied a magnetic field. Now we actually have a formula to describe this. We have a formula to describe the force. The formula goes F is equal to BQV sine theta. Now in this formula, F is the force in newtons, B is the magnetic field strength in teslas, Q is the charge in coulombs, V is the velocity in meters per second, and the theta describes the direction between the magnetic field and the velocity of the charged particles. So we'll be looking in a little minute at how to use this quantitatively, but the other thing we need to consider is how this works as vectors in order to get the direction, because force is a vector. So in order to work out the direction of this force, we actually need to use something called the right-hand rule, which, as its name implies, uses your right hand. So in order to use your right hand, your fingers of your right hand represent the direction of the magnetic field. Now I remember this because when we draw magnetic field lines, we've got lots of magnetic field lines and you've got lots of fingers there. So remember, your fingers point in the direction of the magnetic field. Your thumb points in the direction of the velocity of the charged particles. And then the force is out the palm of your hand. Now I remember this because you can apply a force with the palm of your hand. Now this is the force felt by a positive particle. If you've got a negative particle instead of a positive particle, remember that the force is out the back of your hand instead. So your fingers represent the direction of the magnetic field, your thumb is the direction of the velocity of the particle, and the palm of your hand represents the direction of the force. So let's trial out our right-hand rule now on this setup. So remember that magnetic field lines come out of a north pole. So with your right hand, your fingers should be pointing into the screen. Now if we want to represent that diagrammatically, we can actually represent it by little crosses like this. We do that because we imagine the magnetic field lines like an arrow. If the arrow is coming towards you, you see the point of the arrow. So magnetic field lines coming out of the screen would look like little dots. If the arrow is receding from you, you see the tail feathers receding, so you see little crosses. And so that's how to remember how to represent magnetic field lines going into or out of the page. So we've lined up our fingers with the magnetic field lines. Now your thumb represents the direction of the velocity of these particles, so that's upwards, and these electrons are negative particles. So the force isn't out the palm of your hand, rather it's out the back of your hand. So let's just check that when we bring this north pole towards these cathode rays, they feel a force in this direction, which they do. Now let's line the magnet up the other way. In this case, the magnetic field lines are coming out of the screen towards you, so we could draw those by little dots, and the velocity is still upwards, and so the electrons feel the force in this direction. So this is in agreement with our predictions from the right-hand rule. Let's have a go at a few quantitative examples of using this equation now.
So the question is, a proton is shot with a velocity of 2.00 times 10 to the 5 meters per second into a magnetic field with a magnetic field strength of 5.00 milliteslas. Assume that the velocity and the magnetic field are at right angles to each other.
Part A, draw a diagram showing this situation. B, calculate the force felt by the proton in your diagram. C, what is the acceleration of the proton in this case? D, if the velocity of the proton makes an angle of 30 degrees with the magnetic field, what is the magnitude of the force felt by the proton? Okay, so for part A, let's draw the diagram over here. So we have a magnetic field. These lines should all be parallel to each other and straight, but that's our magnetic field. It's got a field strength of 5.00 milliteslas, and then we're shooting in a proton, so that's a positive charge up here, so that's an angle of 90 degrees. So this shows the velocity v. Now, part B, we need to calculate the force felt by the proton in this diagram. So we can use F is equal to BQV sine theta. Now this is a proton, so the proton charge, so Q is equal to 1.602 times 10 to the minus 19 coulombs, and the mass of the proton, which we'll need later, is equal to 1.673 times 10 to the minus 27 kilograms. Okay, so to work out the force, we need to substitute into this equation here. So B is 5 milliteslas, so 5.00 times 10 to the minus 3, times Q, which is 1.602 times 10 to the minus 19, times V, which we're told is 2.00 times 10 to the 5 meters per second, times sine, and this is 90 degrees. And now sine of 90, that is just equal to 1. So now we can solve this on the calculator. When we type it in, we get 1.602 times 10 to the minus 16 newtons. And so to three significant figures, this is 1.60 times 10 to the minus 16 newtons. And now it's asked us to find the force, not the magnitude of the force, so we should include a direction. So we can use our right hand rule. Line your fingers up with the magnetic field lines, line your thumb up with the velocity, and then your palm of your right hand is pointing into the screen. So for our diagram, as we've drawn it here, it's into the screen. Now, part C says what is the acceleration of the proton in this case. So we're going to need to use Newton's second law, F is equal to ma, which tells us that A is equal to F on m. F we've just calculated, 1.602 times 10 to the minus 16, divided by the mass, which is 1.673 times 10 to the minus 27. This was newtons, this is kilograms. So even though this force seems really small, the mass of the proton is absolutely tiny. So solving this on the calculator, we get 9.58 times 10 to the 10 meters per second, and this is going to have the same direction as the force, so it's going to be into the screen. And then with part D, we're asked if this now makes an angle of 30 degrees, what's going to be the force? And so what we can do is just do F is equal to BQV sine 30. Now this BQV hasn't changed from before. So B times Q times V is still 1.602 times 10 to the minus 16. So this is 1.602 times 10 to the minus 16 times sine 30. And solving that on our calculator, we get 8.01 times 10 to the minus 17 newtons. And this time we have only been asked for the magnitude. If we were asked for a direction, it would still be into the screen. So the question is, a helium nucleus with a mass of 6.64 times 10 to the minus 27 kilograms and a charge of 3.204 times 10 to the minus 19 coulombs enters a region with a magnetic field strength of 10.0 teslas.
The arrangement is shown in the diagram. So here's our diagram. You can see that the crosses mean that the magnetic field is going into the page, and the velocity of our helium nucleus is initially up the page. The speed of the helium nucleus is 3.00 times 10 to the 6 meters per second. A. What force does the helium nucleus initially experience? B. Explain why the helium nucleus experiences circular motion. C. Calculate the radius of the circular path followed by the helium nucleus. Okay, to answer part A, we need to use F is equal to BQV sine theta. And we just need to substitute in here. So the magnetic field strength is 10.0. Q, the charge we're told, is 3.204 times 10 to the minus 19. And V, the speed, is 3.00 times 10 to the 6. And then we need times sine theta. And this sine theta is the angle between the magnetic field, which is into the screen, and the velocity, which is up the screen. So this is times sine 90, and sine 90 is 1. And so what we need to do now is enter this into the calculator, and when we do that, we get 9.61 times 10 to the minus 12 newtons. And this is to 3 significant figures, as everything here is, well, this is given to 4 significant figures, but the magnetic field strength and the mass are given to 3 significant figures. And so now what we need to do is work out the direction, and so point your fingers of your right hand into the screen, your thumb points upwards, and you can see that the force is then to the left, so in this direction. So this is to the left. Now part B. So now we need to explain why this causes it to undergo circular motion. And so you can see that as it's travelling upwards, it feels a force at right angles to the direction it's travelling, which is going to start it moving in this direction. At which point, if we look at this calculation again, it will be feeling the same force, but at right angles to the direction it is now travelling. So this force always remains at right angles to the velocity, and this is because the velocity continues to remain at right angles to the magnetic field. So let's give an explanation. The force, or the acceleration, because they're just related to the mass of the particle, is always at right angles to the velocity of the particle. When acceleration and velocity are always perpendicular, and constant, which they do remain constant in this case, a particle undergoes circular motion. Part C then, we need to calculate the radius of the part. So we know that the centripetal acceleration, mv squared on r, comes about due to this magnetic force here, BQV sine theta. And so this tells us that the radius is equal to mv squared over BQV sine theta. And so the mass we're given up here, 6.64 times 10 to the minus 27. The V is equal to 3.00 times 10 to the 6 meters per second squared over the BQV sine theta, which we calculated here, 9.612 times 10 to the minus 12. And so solving this on the calculator, we get 6.22 times 10 to the minus 3 meters, i.e. 6.22 millimeters.
In this video, you've been introduced to the theory of electromagnetism. So historically, we had a theory of electricity and another theory of magnetism, and then Maxwell managed to combine them into one theory called electromagnetism. So electromagnetism describes lots of electromagnetic formula. After this, we had a look at how to calculate the size of a force on a charged particle in a magnetic field. You saw that this force could be calculated using the formula F is equal to BQV sine theta, and that we can use the right-hand rule to determine the direction of this force on a charged particle.
Thanks to Sebastian Frick for filming this video.